Welcome back to another explainer. Today we're doing something pretty cool. We're going to literally look right through the walls and floors around us to uncover the secret anatomy of buildings. We're taking a journey through the invisible, absolutely relentless forces of physics that keep the modern world standing upright, all relying on the magic of reinforced concrete. Okay, let's dive right into this. Here's our roadmap. We're kicking things off with the perfect partnership. Then looking at the invisible forces, mapping out the anatomy of a building, tracing the load path, and finally shaping the way.
Part 1. The perfect partnership between concrete and steel.
When you look at any modern city skyline, you are basically looking at the ultimate engineering superhero tag team. Seriously, concrete and steel are the perfect duo because they completely cover each other's flaws. Concrete? It's got incredible compressive strength. That means it can handle being squashed or pushed down on by an insane amount of weight. But, and this is a big but, it's kind of weak against tension. It cracks easily if you try to pull it apart or bend it. So, enter steel. Steel has amazingly high tensile strength. When you embed steel bars right inside the concrete, boom, you get reinforced concrete. It's a composite material where the steel handles all the pulling and the concrete handles all the crushing. Literally, one just cannot work efficiently without the other.
But, like any engineering solution, this partnership definitely comes with some trade-offs. On the plus side, we've got that incredible compressive strength, excellent fire resistance, and it's highly economical for massive structures like dams, heavy columns, and deep footings. Plus, you can mold it into practically any shape before it sets, which is awesome. On the flip side, though, this composite material is unbelievably heavy. That immense weight requires even larger columns just to hold itself up before we even start adding anything else to the building. And over time, it's susceptible to shrinkage and cracking if it's not managed perfectly.
Moving on to Part 2, the invisible forces. Let's understand loads. Now, what's really interesting about this is that a building's biggest job is actually just holding up its own massive weight. We call this the dead load. This is the static, unchanging weight of the structure itself. We're talking the heavy concrete floors, the fixed materials like tiles, the mortar, and permanent brick walls. It is a constant, relentless force pulling down on the structure, and it literally never sleeps.
And then we have the live load. Now, unlike the dead load, live loads are completely dynamic and honestly pretty unpredictable. This is all the movable stuff. People walking around an office, furniture getting shifted around, wind pressure hitting the side of the building, maybe the weight of a sudden snowstorm on a roof, or even the violent shaking force of an earthquake. Structural engineering is really a masterclass in anticipating these highly varying, shifting movements.
Check this out. It's actually really surprising when you think about it. You might assume a hospital operating room, packed with heavy medical equipment and personnel, would need the highest live load capacity, right? It sits at 2.9 kilonewtons per square meter. But look at the bottom row. A library stack room needs to support a massive 7.2 kilonewtons per square meter. No way, right? But paper is incredibly dense and heavy when it's stacked tightly on shelves. Engineers have to account for that specific, extreme live load requirement long before the first book ever even arrives.
Section 3, Anatomy of a Building. Let's look at the structural skeleton. So how does a building actually process all of this weight? Let's trace the journey of a load from top to bottom. It's basically a precise mental map that happens in 4 steps. Step 1, the force hits the slabs. Those are your flat horizontal floors. The slabs then immediately transfer that weight to step 2, the beams. You can think of beams as the thick horizontal supports running right under the edges of the floors. Then those beams funnel all that accumulated weight down into step 3, the columns. Those thick vertical pillars you see in parking garages or big lobbies. And finally, the columns push all that combined downward force into step 4, the footings, safely dissipating all that energy deep into the earth. It's just a brilliant, continuous path of gravity.
Section 4, tracing the load path. Let's put the math into reality.
And this brilliantly illustrates how this works in a real-world scenario. Looking at the floor plan here, notice that large area labeled Slab S. That's our floor surface. It rests right on those horizontal framing lines, beam B1 and beam B2. And right there at their intersection is the thick square of column C. Even just glancing at this, you can visually sense how the forces pressing down on that wide, flat slab are naturally going to be directed toward those supporting beam lines, and ultimately forced right onto that single central point of the column.
But before an engineer can move the weight, they have to figure out exactly how much weight there actually is. Calculating the dead load means we have to break the floor down into its physical layers, because, well, a floor isn't just one magic solid block. It's a dense stack. You've got 1 centimeter of tile on top, 4 centimeters of mortar, a thick 12-centimeter belly of heavy structural concrete, and then 2 centimeters of plastering underneath. We literally have to turn this physical reality into exact math.
So here's how engineers stack those individual weights to find the total. They calculate the specific density of the tile, the mortar, the concrete, and the plastering per square meter. They add all of that up and then add in the expected live load for a housing unit, which clocks in at 1.9 kilonewtons per square meter. When you combine that permanent dead load with the varying live load, you get a total combined load of 6.28 kilonewtons pushing down on every single square meter of that floor.
Finally, Section 5, Shaping the Weight, the Geometry of Forces.
So, the crucial point here is, how do engineers turn these wide, flat, super heavy surfaces into calculating tools? Well, the answer is geometry. A flat floor doesn't just dump its weight randomly onto the supports. It actually naturally distributes its weight toward the supporting beams in highly specific geometric patterns. By drawing 45-degree angle lines from the corners of a rectangular slab, engineers can see exactly how the floor mathematically breaks itself into distinct triangles and trapezoids of weight, all basically leaning against the specific beams around the perimeter.
But here's the catch. Calculating the varying stress of a triangular or trapezoidal weight along a beam is frankly incredibly complex. So structural engineers do a bit of mathematical magic. They use conversion formulas to transform those complex peaked triangular and trapezoidal load distributions into flat, smooth, rectangular equivalent loads. It's a really neat trick that makes calculating the required strength of the beam much easier without sacrificing any safety or accuracy.
Let's move to this next view and see how this builds up in an actual floor plan. Notice how those geometric areas from the slab are actively pushing their specific portions of the load onto beam B1 and beam B2. Now I want you to imagine stacking everything we've talked about so far. We've got the weight of those floor slab geometries, the weight of the thick brick walls sitting directly on top of the beams, the heavy concrete weight of the beams themselves, and even the cascading weight of the floor above this one. All of these forces are funneling together, traveling horizontally down the beams, and just converging brutally on one single critical point, column C.
When engineers actually run all the complex calculations from our source example, mathematically combining those dead loads, the live loads, the walls, the beams, and the floors above, they reach a staggering total, 232.5 kilonewtons. Guys, that is roughly 52,000 pounds of force. That's the massive, invisible weight that just one single 20 by 20 centimeter column in this theoretical building is quietly and reliably holding up right now. It really gives you a profound, almost dizzying appreciation for the precise engineering hidden right inside the walls.
Which leaves us with this final thought. Take a look at the ceiling above you right now and the floor beneath your feet. What invisible forces is the building you're in right now successfully holding up? Keep asking questions, keep looking past the surface, and I'll see you in our next explainer.